In this video, we're going to talk about derivatives of polynomials and the function e to the x. So to begin with, we're going to talk about what is the derivative of a constant. So we're going to let f of x be equal to c, where c is a constant. Now this shouldn't come as any surprise, but we'll see the derivative is 0. Now if we use the definition, we have that the derivative equals the limit as h goes to 0 of f of x plus c plus h, minus f of x divided by h, which equals then the limit as h goes to 0. F of x plus h will just be c, because you always get c out of this function, minus c divided by h. So we have the limit as h goes to 0 of 0, which is just 0. Now this shouldn't be any surprise that the derivative of a constant is 0, as remember that the derivative is the rate of change of the function, and constant functions never change in value, so you'd expect the rate of change to be 0. So now we want to deal with power functions. So in case you don't remember what a power function is, a power function is a function of the form f of x equals x to the n for some real number n. Now we're going to deal with natural numbers to start with, and then we're just going to kind of wave our hands at what happens beyond that. And so we're going to assume n is a natural number. And so we want to take the derivative of the function f of x equals x to the n. So we have f prime, and I'm going to use the second definition of the derivative. So f prime of a is the limit. So x goes to a of f of x minus f of a, all divided by x minus a, which equals the limit. So x goes to a of f of x, which is just x to the n, minus f of a, which is a to the n, divided by x minus a. So we have the limit as x goes to a. Now, just like normal, we want to factor the numerator. Now, the numerator, I'm going to say how it factors and explain it. So it factors as x minus a times x to the n minus 1 plus x to the n minus 2a plus x to the n minus 3a squared, and so on to a to the n minus 2x times a to the n minus 2 plus a to the n minus 1. And then that's all divided by x minus a. Now a good way of seeing why this is how the numerator factors is if you think of distributing the x across the top, you'd have x to the n plus x to the n minus 1a plus so on up to x a to the n minus 1. That's from distributing the x to everything. And then if we distribute the a to everything, we're going to get negative a x to the n minus 1, negative x to the n minus 2a squared, and so on to negative a to the n. And then notice that things cancel off. The x to the n minus 1 cancels with a to the x n minus 1. This x a to the n minus 1 will cancel off with something in the dot, dot, dot. And x to the n minus 2a squared will cancel off with something in the dot, dot, dot. And so we're just left with x to the n minus a to the n. And so just actually doing this product, we see that it does factor as I claimed. And so in the limit, we have x goes to a. Now we can cancel off the x minus a's to be left with just x to the n minus 1 plus x to the n minus 2a, and so on up to x to the times a to the n minus 2 plus a to the n minus 1. And now this is a polynomial, which is continuous, so we can just plug a into everything. So we're going to have a to the n minus 1 plus a to the n minus 2 times a, and so on, a times a to the n minus 2 plus a to the n minus 1. And now this is just going to be a bunch of a to the n minus 1s added up. And now the question is, well, how many of those terms did we have? And you can keep track based on the exponent on a in the factorization. So in this first term, we had the exponent of 0, then a has exponent 1, then 2, up to n minus 1. So we have from 0 to n minus 1 terms, and adding those, counting, that's just n things. So in total, we have n a to the n minus 1s in the sum. So we get n a to the n minus 1. So in other words, we found that the derivative of x to the n is n x to the n minus 1 when n is a positive integer, or a natural number is the way I phrased it a minute ago. Okay, now the reason why this is helpful is we did all of this kind of symbolic manipulation because it'll let us now compute derivatives much faster. And so if we wanted to compute the derivative of something like x to the 6th, rather than having to go through the whole limit definition, we can just use the rule we just found, because that works for any n. So this derivative is just 6x to the 5th. And similarly, if I took the derivative of x to the 1000th, this is 1000 x to the 999. And so we're able to compute these derivatives much easier by doing this property. Now, we don't have all of the tools to justify the next thing that we're going to mention, but this rule actually applies when n is any real number, and so this is what's called the power rule. So the power rule for derivatives says if n is any real number, then the derivative of x to the n equals nx to the n minus 1. We will need to develop more ways of doing derivatives before we can fully justify this, but typically in a Calculus 1 class, you just introduce the power rule at this point, and you just say you can use it from that point on. But this allows us to compute derivatives when we don't necessarily have an integer in the exponent. So for instance, if we wanted the derivative of 1 over x cubed, well, this is the derivative of x to the negative 3, just using exponent properties. And so this is negative 3x to the n minus 4. So the derivative would be negative 3 over x to the 4th. And so that would be the derivative of 1 over x cubed. And if we wanted to take the derivative of something like the cube root of x to the 5th, well, this would be the same as x to the 5/3. So we want the derivative of x to the 5/3. So we'd have 5/3 x to the 2/3. Just bringing the exponent down and subtracting 1. And so our exponent was 5/3. So we brought that down in front, then 5/3 minus 1 is 2/3. And so we can compute derivatives much faster using this power rule. So one more example to keep in mind is that we can compute tangent lines using derivatives. That was kind of the whole motivation for derivatives. So let's look at the following example. So we want to find the equation of the line tangent to y equals x, square root of x, at the point 1, 1. And so we've talked about how to do this before. We want to find the derivative at the value of 1 and then use that in the point slope formula. But rather than going through the kind of long process of using the definition of the derivative, we have f of x equals x square root of x, and that's just x times x to the 1/2, which is x to the 3/2. So using the power rule, we have that the derivative of this function is going to be 3/2 x to the 1/2, bringing the exponent down and subtracting 1 from it. And so that gives us our derivative right there. And now we just need to know what the derivative is at 1. And so we have f prime of 1. So I'm just going to plug 1 into our function. And we get out 3/2. So the slope of our tangent line will be 3/2. And we were able to figure this out without having to compute any limits, just by using this power rule that we derived before. So now we can use the fact that we know the slope and we know a point. So the point slope form tells us we are going to have y minus 1 equals 3/2 times x minus 1. And we want to solve for y. So we get y equals 3/2 x minus 3/2 plus 1. So our tangent line is y equals 3/2 x minus 1/2. And so this then gives us our tangent line. So we were able to figure out the tangent line to this curve y equals x square root of x without actually having to compute any limits. We just used the power rule to figure out the derivative. So the next thing we want to mention, as we want to expand to any polynomial, is we want to be able to deal with if we are adding, subtracting, and scaling functions. And so recall that we have the following limit properties. The limit as x goes to a of c times f of x equals c times the limit as x goes to a of f of x. The limit as x goes to a of f of x plus g of x equals the limit as x goes to a of f of x plus the limit as x goes to a of g of x. And the limit as x goes to a of f of x minus g of x equals the limit as x goes to a of f of x minus the limit as x goes to a of g of x. And it turns out, using these three limit properties, we get very similar results for derivatives. And so we have the following theorem. And so if f and g are differentiable with c being a constant, then we have the following. The derivative of f of x plus g of x equals the derivative of f of x plus the derivative of g of x. Second, the derivative of f of x minus the g of x equals the derivative of f of x minus the derivative of g of x. And third, the derivative of a constant times f of x equals that constant times the derivative of f of x. So what these are saying is we can split up derivatives over addition, subtraction, and we can pull scalars out. Now I'm not going to justify all of these rules, but I am going to justify the first one. The justification for the second and third goes very similar to what we're about to do with the first one. So we want to prove that if I take the derivative of f of x plus g of x, it equals the derivative of f plus the derivative of g. So we have f plus g's derivative at x That's just a short way of writing the derivative of f of x plus g of x. This would be the limit as h goes to 0 of f plus g evaluated at x plus h minus f plus g evaluated at x divided by h, which is the limit as h goes to 0 of f of x plus g of x plus g minus f of x plus g of x, all divided by h, which equals the limit as h goes to 0 of f of x plus h plus g of x plus h minus f of x minus g of x, all divided by h. And now all we're going to do is we're going to rewrite this expression. So this equals the limit as h goes to 0 of f of x plus h minus f of x divided by h plus g of x plus h minus g of x divided by h. And now we can do this as we're just basically splitting up the fraction into two pieces. So I've rearranged the order I was doing my combination of addition and subtraction in the numerator, and then I just split the fraction into two fractions. Because they have a common denominator, we can do that. But now we know that f and g are both differentiable. And so we know the limit will exist, so we can split this limit into two pieces. So if the limit is h goes to 0 of f of x plus h minus f of x divided by h, plus the limit as h goes to 0 of g of x plus h minus g of x divided by h. And this right here is f prime of x, and this piece right here is g prime of x. So what we found is that f plus g prime of x equals f prime of x plus g prime of x. So as claimed, we can split up the derivative over addition. The argument for subtraction is almost identical to this. The only difference is that we just have a subtraction instead of f plus g, we have f minus g. So you have to be a little careful with your negative signs, but the same argument works. And for a constant, it's even easier as you literally just factor the constant out of everything. And so we then have these three properties for derivatives. And using these properties, we'll be able to compute the derivative of any polynomial. So I keep saying this term polynomial. If you don't remember what a polynomial is, we're going to define it right now. So a polynomial is a function of the form a n x to the n plus a n minus 1 x to the n minus 1, and so on, plus a 1 x plus a0, where a0, a1, up to an are all real numbers. So this looks kind of complicated, but it's basically just saying we have a bunch of power functions added together, multiplied by constants. And so we know how to deal with addition, subtraction, and multiplying by constants. And the power rule lets us deal with any power function. And so we can deal with any polynomial. In fact, we can deal with more than just polynomials, as polynomials require that we have natural numbers in our exponents, and we can deal with it when it's not a natural number as well. So let's look at some examples of this. So we want to find the derivative of f of x equals 7x to the 6th plus 4x to the 5th plus 2x squared plus 9x minus 11. So if we want to compute this derivative, we're going to do it in pieces. So the derivative of f is going to be the derivative of this whole expression. So we have 7x to the 6th plus 4x to the 5th plus 2x squared plus 9x minus 11. And now we're going to break up over addition and subtraction. So this is the derivative of 7x to the 6th plus the derivative of 4x to the 5th plus the derivative of 2x squared plus the derivative of 9x minus the derivative of 11. And now we can pull constants out. So this is 7 times the derivative of x to the 6th plus 4 times the derivative of x to the 5th plus 2 times the derivative of x squared plus 9 times the derivative of x minus the derivative of 11. So now we're going to compute each of these derivatives. So this is 7 times the derivative of x to the 6th will be 6x to the 5th, plus 4 times the derivative of x to the 5th is 5x to the 4th, plus 2 times the derivative of x squared, which is 2x, plus 9 times the derivative of x, which is 1, minus the derivative of a constant. And we started out with the derivative of a constant, so we know it's 0. And so we just need to multiply these together. So we get 42x to the 5th plus 20x to the 4th plus 4x plus 9. And so that then is our derivative. And so we were able to compute this derivative of this rather complicated looking polynomial just by using the facts that we have. So just plugging things in using the power rule. Now, as I mentioned, we can actually go beyond polynomials. And so if we wanted to find the derivative of g of x is equal to 4x cubed minus 4x plus 3 square roots of x. If we wanted to compute this derivative, this isn't a polynomial, but we can still find its derivative. The derivative is going to be the derivative of this expression. So we're going to have 4x cubed minus 4x plus 3 square roots of x. And then we can split this up. So the derivative of 4x cubed minus the derivative of 4x plus the derivative of 3 square roots of x. And now remember, this 3 square roots of x, this is just 3x to the 1/2. And so this becomes 4 times the derivative of x cubed, which is 3x squared, minus the derivative of 4x is 4, plus 3 times the derivative of x to the 1/2 is 1/2 x to the minus 1/2. And so we get 12x squared minus 4 plus 3/2 x to the minus 1/2. And so we were able to compute this derivative just going through the power rule like we just barely talked about. Now we're going to consider the case of exponential functions. So we're going to look at the function f of x equals b to the x, where b is some value greater than 1. So we want to find the derivative. So we have f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x divided by h, which is the limit as h goes to 0 of b to the x plus h minus b to the x divided by h. Now we're going to factor b to the x out of the top of everything. So it's multiplying both of these terms. To see that a little bit clearer, you can write this as b to the x times b to the h minus b to the x over h. So we have the limit as h goes to 0 of b to the x times b to the h minus 1 divided by h. Now at this point, b to the x is independent of the limit. The limit's only as h goes to 0. So this equals b to the x times the limit as h goes to 0, of b to the h minus 1 over h. And now this limit that we have right here, this is just going to be f prime of 0. That's just using the definition of the limit. You can check that's of the derivative. You can check that's f prime of 0. So we get b to the x f prime of 0, which is f of x times f prime of 0. And so what we found then is the derivative of b to the x is just going to be b to the x times the slope of the tangent line at 0. So that's nice, other than we don't know the slope of the tangent line at 0. So this is where a special fact comes in. Now the number e is defined so that the slope of y equals e to the x is 1 at x equals 0. So that's just a definition of the number e. And because of that, we have that the derivative of e to the x will be e to the x times its slope at 0, which is 1, so it's e to the x. So the derivative of e to the x is e to the x. So this is a special fact for the function e to the x. And so just to make this a little bit more clear, if f of x is the function e to the x plus 3x, then the first derivative of this function would be the derivative of e to the x plus 3x, which is the derivative of e to the x plus the derivative of 3x. E to the x is the derivative of e to the x, and the derivative of 3x is 3. And so we have that the derivative of e to the x plus 3x is e to the x plus 3. And if we take the second derivative, this is going to be the derivative of e to the x plus 3, which is the derivative of e to the x plus the derivative of 3. The derivative of 3 is 0. The derivative of e to the x is e to the x. So we get e to the x is the second derivative of the function e to the x plus 3x. So now the last thing we want to do is talk about the following example. So we want to find at what point on the curve y equals e to the x is the tangent line parallel to the line y equals 2x. So if we draw a picture of this situation, what we have here is we have the graph of the function y equals e to the x. We have the graph of 2x, which looks something like the following. And so we just want to find a point on the graph, which would be, say, the point like right here, where the tangent line at that point is parallel to the line y equals 2x. And so that means that the slope will be 2. So we want to find the point on y equals e to the x, where the tangent line has a slope of 2. Well, the derivative of e to the x is e to the x, and so we just really want to know for what value e to the a equals 2. So we want to know for what value of a, e to the a equals 2. Well, by definition of natural log, that is when a equals ln of 2. ln of 2 is defined to be the number you need to raise e to in order to get 2. So a is ln of 2, and so therefore, our point is just going to be ln of 2, and then e to the ln of 2, because that's the point on the graph. So it's ln of 2, comma 2, because e to the ln of 2 is the number 2.